To map the expansion of the universe, astrophysicists rely on a cosmos that behaves with clockwork predictability. They operate within the rigid confines of the Standard Model, a set of laws that defines how stars live and die. Measuring the immense distances between galaxies requires a specific, reliable benchmark, the Type A supernova. Because these stars theoretically always explode with the same peak brightness, they serve as the ultimate cosmic measuring sticks. If the source brightness is a known constant, astronomers can determine distance by measuring how much that light has faded before reaching our telescopes. The entire architecture of modern astrophysics assumes this rule of uniform brightness is absolute. That assumption was recently tested in a small satellite galaxy on the edge of the Large Magellanic Cloud. Roughly 160,000 light-years away, a star exploded in a way that defied every standard calculation. Data from the event shows a peak brightness reaching triple the limit of a standard Type AA supernova. The total energy released was measured at 1.5 times 10 to the power of 44 joules. This single explosion generated 100 times the energy our Sun will emit over its entire 10 billion-year lifespan. According to the current Standard Model, an explosion of this magnitude and intensity is a mathematical impossibility. Astronomers tracked this star for 3 years before it detonated. Based on its faint signal, they initially categorized it as a typical dim white dwarf. However, optical telescopes like Hubble struggle with interstellar dust, which acts as a thick veil, obscuring the actual physics of the explosion. Relying on visible light alone made it impossible to see the mechanics breaking the rules. To find the truth, researchers utilized the near-infrared capabilities of the James Webb Space Telescope. Infrared imaging allows us to look through the dust clouds and examine the chemical remnants of the explosion directly. This high-resolution view of the wreckage reveals a chemical signature that contradicts the old theory. The spectral data shows carbon and oxygen levels that vastly exceed the standard estimates for a Type Ia explosion. Furthermore, the rate at which the star shed its mass during the blast was 5 times higher than the Standard Model allows. The chemistry of the debris confirms it. This is not a standard supernova. It is a new category of cosmic event. Explaining this impossible data requires a new hypothesis for how stars can die. This new model describes an asymmetric merger, 2 entangled white dwarf stars spiraling into a lopsided, violent collision. This unstable merger triggers a high-velocity ejection of matter, fueling the extreme brightness and energy that the telescopes recorded. The discovery suggests the universe is far more chaotic and unpredictable than our established models assumed. If these violent mergers are more common than we thought, we must now learn to identify these bright imposters when measuring the expansion of the universe. Our current maps of the cosmos are not final. They are working frameworks waiting to be refined by new technology. Every time we look deeper into the sky, we discover a reality that outpaces what we have already mapped.